The task of AT3 was to put us on to help design and engineer a wind turbine, which is to be set on the Bellarine Peninsula. The use of wind turbines will help reduce the carbon emissions in Australia by using a renewable energy source. We were set to calculate and engineer the specifications of the wind turbine that's needed to maximise the performance and increase the energy creation potential. These goals will be completed by identifying the height of which the wind turbines will be made at, the number of blades that are best fit, along with the size of these blades. We also will have to develop a level 3 material that will meet the strength and axial requirements, which also are well suited for the end of life of the turbine if it is ever to be recycled. Lastly, as engineers, we will have to use our expertise to develop and design a support structure with relevant materials which will hold up the main components of the turbine, this being the turbine and its blades. The requirements for the project are to design a wind turbine without the analysis on wing shape and flex ratios from the blades in order to simplify the project. The stakeholders of this project include people in nearby housing and also the council. Residents would prefer a turbine that operates quietly and does not obstruct their land and lives to an extravagant level. Councils, on the other hand, would like a turbine that produces clean, renewable energy and reduces their overall CO2 footprint. The project insists that we must not exceed the length to depth ratio for the blades and column, thus being 120 metres, to ensure the blades are not longer than the column, whilst also producing an efficient design that generates the maximum amount of power for minimum environmental cost. This will all be solved by going through significant planning and development to create the best possible solution. This will most likely be completed through software, which will help calculate what aspects produce the best performance. Along with, we will do materials research to determine which materials would be the best for this project.
Material properties. The wind turbine project requires considerate research into material selection in order for turbine blades to meet power generation goals and strength requirements, as well as withstanding the vertical axial loading on the tower column. For the tower in particular, supporting itself, turbine blades, generator and transmission unit requires a material with significant compressive strength and will be crucial to its success. Its ability to withstand tensile loads, however, will have little advantage in the depth of analysis required by Assessment Task 3. Tensile strength will instead be essential in the construction of the turbine blades, where whilst in operation will encounter a centrifugal force attempting to pull the blades from the tips outward in combination with their own weight force when pointing below the horizon, ultimately generating a significant tensile load on their chosen material. Corrosivity of the material will be of utmost importance in Assessment Task 3, with the wind turbine being subject to all manner of weather conditions during its operation. The corrosion causes material to become brittle and flake, ultimately leading to a reduced cross-sectional area and weakening of the component. Any corrosion that does occur over the turbine's targeted 30-year operating span will need to be minimised through maintenance, however minimal restorative action is desired by the task. Form and design optimisation. Design optimisation is the process of making the form of the design, or in the case of Assessment Task 3, the cross-sectional area optimal for the loads that will be applied. Design optimisation can take into account a variety of factors. Optimising to reduce the mass of unnecessary and excess material that constitutes both the blades and the tower of the wind turbine is beneficial for a variety of reasons. This includes that less material makes components more environmentally conscious, as well as less costly to obtain with lower quantities of raw resources needed. Further, removing mass from the turbine blades, in particular, will increase efficiency with reduced energy required to overcome inertia. Although not particularly relevant to axial loads, it is good practice to understand design scenarios that induce stress concentrations, such as square or extremely tight radius corners. By implementing what is known as a fillet and creating a radius within an internal corner, stress is less concentrated to vertices, reducing likelihood of failure. Load types. Within Assessment Task 3, the primary forces we will be observing and ensuring the design and chosen material can handle are axial loads. Axial loads occur when a force is applied acting perpendicular to the cross-sectional area, as seen in compression and tension tests, in which the turbine blades will undergo both tensile and compressive loads during stasis and operation, whilst the tower will only be in compression. The maximum compressive load acting on a blade will be during stasis, and that of the tower can be calculated by mass times gravity. The The maximum tensile load acting on a blade will be during operation and can be calculated by self-weight vertical plus centrifugal force. The stress produced by these axial loads can then be calculated by the formula stress equals force over area.
Wind turbines do have a significant environmental impact throughout their life cycle, from production to end of life considerations. The energy and environmental costs to produce, manufacture, and transport wind turbines is actually pretty big. The manufacturing process involves the extraction and processing of raw materials such as steel, fiberglass, and rare earth metals, which requires energy inputs and results in carbon emissions. Transportation of these large components to the installation site also contributes to the environmental footprint, especially if the site is long distance. Once installed, the wind turbine should have a lifespan of around 30 years with minimal maintenance. Materials with low embodied energy are preferred to reduce the overall environmental impact. We can lessen regular maintenance through the use of stronger materials. But at the end of their life, wind turbines do present a challenge for disposal. Traditional methods such as landfill dumping are just not environmentally sustainable. Instead, adopting a circular economy principle is very important. This involves minimizing waste and maximizing resources by reusing, repairing, recycling, and repurposing products and materials. For instance, metals can be recycled and composite materials can be repurposed or processed into new forms. Applying a circular economy to wind turbines means making them last longer, using parts that can be easily fixed or upgraded, and reusing old parts. Materials from old turbines can be recycled, and non recyclable materials can be turned into energy. By focusing on sustainable end of life strategies, the environmental impact of wind turbines can be significantly reduced, ensuring that they remain as a form of green energy. As for advice, we believe it's good to share your ideas with your team and use all the available resources there are online. We should focus on the key concepts from class like material science, force load, structural analysis, and use free body diagrams to explore the forces acting on the turbine. Having a visual representation can help get the idea across to your peers or your future boss or clients. Other potential areas for research could involve wind data analysis and site conditions for the Bellarine Peninsula. This can help us to find the best turbine placement for performance and efficiency. We could also study the aerodynamics of the wind turbine blades to optimize the shape and size for the required power output. Well, if you enjoyed that video, make sure to like, comment, and smash that subscribe button. See you later, Turbinators.